Okay, so if we have already changed the title to 7.1, the general solution, if you turn to the top of page 573, there's space at the top of page 573. We're going to do a bunch of solving theta questions just as a warm-up, so you can fill page 573, and then we'll continue from there. So, first of all, here's our warm-up. We're going to solve in radians between 0 and 2 pi. 3 sine theta equals -2. And I'll give you a head start for this one. I'll slide it down here. So if you get ahead far enough, you can start part B already. So make sure you have your calculators out. This would be a calculator question because 2/3 is not on your unit circle. You're going to have to find your reference angle. So we get sine by itself. Find your reference angle. And remember, when finding your reference angle, it's based on an actual triangle with actual lengths, so you're always using positive values when finding your reference angle. So you would have done sine inverse of positive 2/3, not negative 2/3 when finding that reference angle. But then you would have said, well, since sine is negative in quadrants 3 and quadrants 4, so then you could find your answers in quadrants 3 and quadrants 4. All right, let's see how you did on that second one. Get tan by itself, move the 3 over, divide by 8. Find your reference angle by doing tan inverse of positive 3/8. And then since tan is negative, you look in quadrant 2 and quadrant 4. So those first two warm-up ones were calculator ones. Your next two are non-calculator. For the first one, when you get cos by itself, you get cos equals 4, which is bigger than 1. If you tried to draw that triangle with an adjacent side of 4 and a hypotenuse of 1, it would be impossible. So anytime sine and cos, you get an answer bigger than 1 or less than -1, it's going to be a non-calculator question because you're just going to be able to say it's not possible. And the last one that we have, is √3 tan theta plus 1. So if you get tan theta by itself, you get -1 over √3. This is non-calculator because -1 over √3 is on your pie plate. But on your pie plate, we didn't write it as -1 over √3. What did we write it as? Right? If you rationalize the denominator, this is the same as -√3 over 3. So one of the skills that you have is knowing how to rationalize a denominator, and you may get ones that appear in a different form than that is on your unit circle. Because it's non-calculator, then you'd say, I need to manipulate this to make it match. And so now that I see that it's -√3 over 3, I can say my reference angle is part of my pi over 6 family. Tan is negative, so it's going to be in 5 pi over 6 and 11 pi over 6. So these first 4 questions were review of solving, right? We've done this before. We're solving between 0 and 2 pi. That's much of what Chapter 6 was about. What Chapter 7 adds is it says, What happens if we don't restrict the domain and don't say just solve between 0 and 2 pi? What would it mean if you had to solve between 0 and 4 pi? Well, if I had to solve this same question between 0 and 4 pi, then I'd go around my circle twice. So I would still have 5 pi over 6 and 11 pi over 6. But on the second time around, I'd have an angle that's coterminal with 5 pi over 6 and another angle that's coterminal with 11 pi over 6. So then they say, well, what happens if we went between 0 and 6 pi? Well, then I'd have one at 5 pi over 6, one at 11 pi over 6. Second time around, another one coterminal with 5 pi over 6, another one coterminal with 11 pi over 6. And then the third time around, another one coterminal with 5 pi over 6, and another one coterminal with 11 pi over 6. Well, what if we didn't put a restriction on the domain, and we said, you could go around forever. You could list them all. What would that look like? And that is what makes what we're doing today new. That's what we're adding on to what we've already done. So we're going to do these same kind of questions that we've done before, but we're going to call it and look at the general solution when there's no restriction on the domain. So you have space at the top of page 574 for this. So what does it look like for us to find the general solution? Well, the general solution for solving trig equations is just putting together two concepts from chapter 6 that you already know. You already know how to solve like normal from 0 to 2 pi. And so that's how you're going to start. You're going to solve your equation just like we've solved all these other ones, find our reference angle, use the cast rule to find the quadrants, and write our answers from 0 to 2 pi. Then, since you can go around the circle infinite amount of times, every time you go around a circle one more time, you have more answers that are coterminal with our last answers. And if you think back in chapter 6, how did we write all the coterminal angles for something? Well, we added 360 degrees times k, or we add 2 pi times k to write all of our coterminal angles. So step 2 here, by adding 2k pi, which is just 2 pi times k, but we tend to put the k in between the 2 and the pi just to mix things up a bit. Adding this in that green box, that makes you write every single coterminal angle. So if I go back to our question here, I've solved between 0 and 2 pi normally, then my final answer for the general solution would be my 5 pi over 6 plus 2k pi. That writes all of my answers coterminal with 5 pi over 6. And 11 pi over 6 plus 2k pi, that writes all of my answers coterminal with 11 pi over 6. And this is how we're going to write our answers for the general solution. We're going to find our answers between 0 and 2 pi first. Then we're going to take our answers from 0 and 2 pi and add 2k pi. Because if I add 2k pi, that would go all the way around and end in the same place as the one from before. Okay? So here's our first example. And in fact, if you go down to your page 574, you can put an X through their example 1. We're not going to do that example. And this will be the example 1 that we're going to do instead. General solution questions look like this. Sometimes they say solve for theta, where theta is an element of the real numbers, like this one. That's telling you you have to give every single answer. It's a general solution. And sometimes the questions say find the general solution for theta, which means find all the answers. So step 1, we solve this equation, 7 sine theta plus 1 equals 0, like a normal equation from 0 to 2 pi. I would get sine theta by itself, so I move the 1 over, divide by 7, and then I would find my reference angle by doing sine inverse of positive 1/7. Once I have that reference angle, well, sine is negative in quadrants 3 and 4, so I would go pi plus my reference angle to find an answer in quadrant 3, and 2 pi minus our reference angle to find an answer in quadrant 4. That's step 1 in a general solution, solving it like normal. We just solved between 0 and 2 pi, just like our warm-up. This would be a calculator question because 1/7 is not on our unit circle. Step 2, to write the general solution, all you do is take your answers that you got from 0 to 2 pi and add 2k pi to them. If the question was in degrees, you'd add 360 degrees times k. Here's a question for you to try. I just have the answer up here, so if you've got your answer, you can check. If you're still working on it, keep going. And the last example we're going to do today is combining a bunch of things that we've learned already. So here's another quadratic trig function. We have tan squared plus 3 tan theta minus 7 equals 0. If you tried to factor that, you'd try for a long time and find out it is not factorable. So you'd have to go to your formula sheet, and on your formula sheet they have for ax squared plus bx plus c equals 0, x equals negative b plus or minus the square root of b squared minus 4ac over 2a. That's your quadratic formula. So for this one, it's not x squared, it's tan squared. So when using your quadratic formula, it would be tan theta equals, not x equals, negative b plus or minus b squared minus 4 times a times c divided by 2a. Simplifying this, we get negative 3 plus or minus the square root of 9 plus 28, 37 over 2. Definitely not on our unit circle. So we're going to split this up, and we have two equations. We have one equation which would be negative 3 plus the square root of 37 over 2, and one equation that would be negative 3 minus the square root of 37 over 2. Question: is this positive or negative? Negative 3 plus the square root of 37 over 2. Because that's going to make a difference, because we always find our reference angle with positive values. So when I go to my calculator here, on the left-hand side, I need to recognize that negative 3 plus the square root of 37 is positive. So when I go tan inverse negative 3 plus the square root of 37 divided by 2, I get a reference angle of 0.995. the left-hand side, negative 3 minus the square root of 37 over 2, that is negative. So when finding my reference angle for that one, again, I do tan inverse. If I didn't change the signs, I'll push enter, I'll get a negative angle. Reference angles are always positive. So what I need to do is I need to multiply that fraction by a negative number to make it positive. I could either multiply the top by a negative, which would make it positive 3 plus the square root of 37, or I could multiply the bottom by a negative. I think I'm going to do that because it's going to be easier just to insert a negative on the bottom. And now when I find my reference angle, it's positive 1.354. So you might say, can I just, Mr. JR, can I just make whatever negative answer positive? Does that always work? Yes for sine and tan, but no for cos. So it's best to always do tan inverse of the positive value. Our reference angle here, 1.354. So to solve, here tan was positive. It's positive in quadrant 1 and quadrant 3. So you would go pi plus, so I would go to my calculator, pi plus, and if you have one of the newer calculators, another thing you can do is you can scroll up to an old answer and push enter on it, which is kind of handy, 4.14. And over here, tan is negative, so you would be looking in quadrants 2 and quadrants 4. I'm going to go back to this reference angle and store it as x. So I can go in quadrant 2, it would be pi minus x. In quadrant 4, it would be 2 pi minus x. So 1.79 and 4.93. So for my final answer as a general solution, I would write all 4 of them. It doesn't matter if you write them in numerical order. You add 2k pi to each of them. Draw a straight line, which means such that k is an integer. So questions from your notes that you can do for practice are 5, 6, and 9.